Hello guys, trust you're having a nice time and welcome to this exclusive episode of this non-flow process that we have been treated in the last episode. We treated the isobaric process, that is the constant pressure process, and we have also treated the isochoric process, which is the constant volume process. So in this tutorial video, we'll be looking at the adiabatic process and the polytropic process. So it sounds ambiguous, but it's not hard, it's not difficult. From the definition, you can denote exactly what we mean by adiabatic process. So what is an adiabatic process? An adiabatic process is a process during which heat is prevented from crossing the boundary of the system. So it's more like heat is trapped within the system. So meaning that the change in heat is zero. Okay? So mathematically I can write that Q is equal to 0, and from the first law Q plus W is equal to U2 minus U1, where Q is equal to 0, W is equal to U2 minus U1, and this is for the steam. This is for the steam stage. Yes. The steam, and also W will be equal to MR. Okay, W will be equal to mCv T2 minus T1, just like the constant volume process. There it was the Q, that was U2 minus U1, but now since Q is 0, it's now MW, that will be mCv T2 minus T1. So having said this, we can have that for a polytropic process too. We can also have that for a polytropic process. We can have that expanded work, to 1 PV raised to power n is a constant. Okay, so that's P 1V1 raised to power n is P2 V2 raised to power n. So hence we can have our work equation as this: work done is equal to minus 1 to 2 P the V over N, okay, minus 1. So that's after the integration, we have that P2 V2 minus P1 V1 all over n minus 1. This is for steam, and you know that if W is equal to PV, PV is equal to what? MRT. So W being equal to P change in V will be MR change in T. So hence W will be equal to MR T2 minus T1 all over n minus 1. So without wasting much time, let's take a look at the question or some questions under this to help warm things up. So let's look at this question. Yes, a mass of 0.9 kg of fluid. Remember the word fluid. It can be liquid, it can be gas. Okay. Initially at a pressure of 15 bar, 250 degrees Celsius, expands reversibly and isentropically. Remember the word isentropically too. To 1.5 bar. Find the final temperature, work done, and the heat transferred. So the first thing you do is to bring your parameter. You bring out your parameter. Okay. You say parameters given. Parameters given. Mass is equal to 0.9 kg. Initial pressure, that is P1, is 15 bar. T1, 250 degrees C, and it expands reversibly and isentropically. So what is an isentropic process? Isentropically means it expands reversibly adiabatic. So because an isentropic process, can I say this? An isentropic process is a reversible adiabatic process. Okay, so now remember our T2 is 1.5. I didn't write it, so P2 rather 1.5 bar. So they said a fluid. So a fluid now we'll make two assumptions just like we did in some other videos before. So a fluid can either be a vapor or a perfect gas. So assuming it to be a vapor. So assuming the fluid to be a vapor, so we have that. Remember, Q is equal to what? Ts1 minus S2. If Q is equal to 0, S1 is equal to what? S2. No change in entropy. So from the saturated vapor table sorry for my voice, I've been talking a lot. From the saturated vapor table, at pressure 15 bar, we have that the saturated temperature is 198.3 degrees C, which is lower than 250 degrees. So T1 is greater than Ts. Okay, hence the steam is superheated. Okay, hence the steam is superheated. Okay, so from the superheated steam table, now you go to the superheated steam table. So now from the superheat table, we have that is at 15 bar 250 degrees C. We have that internal energy is 2697 kilojoules per kilogram. Okay, the entropy is equal to 6.711 kilojoules per kilogram Kelvin. Alright, now at state 2, P2 is equal to 1.5 bar. So remember that S2 is equal to S1, which is this we have here. So from the saturated vapor pressure, we go back to the saturated vapor pressure. There is vapor table, sorry. Now under 1.5 bar, check for the SF. We have the SF under 1.5 bar to be 1.434. Then SFG will be 5.789, all in kilojoules per kilogram Kelvin. Okay, so remember our formula remains the same. S is equal to SF plus X SFG. Now how do we get the dryness fraction? We already know our S2, which is 6.711, which is equal to, we have our SF plus some unknown dryness fraction, 5789. So doing the necessary calculations, we have that 5.297 will be equal to 5.789 x2. So x2 will be equal to 0.9115, like the dryness fraction. Okay, so now we have our dryness fraction at the state 2. We can compute our enthalpy. So still at the saturated table, at P equal to 1.5, you get your HF, which is 467 plus 0.9115. HFG, that is 2226. So H2 is my H2 will be, the answer you get is your H2, though is not needed. But whatever you get, you write it down. All we need is the internal energy. Okay, so for the internal energy now, you can say U2 is equal to UF plus X UG minus UF. So U2 now will be, so still the value of UF, you get it, from the table. UG, you get it from the table. You get it from the table. So finally U2 is 233.7.4 kilojoules per kilogram. Now we have found our internal energy. So they said find the final temperature. So the final temperature is the temperature. The final temperature is temperature at P2 equals 1.5 bar from the table, which is 111.4 degrees C. Okay, now they said we should find the work done. So you know that the work done is equal to U2 minus U1. So but we have our mass, so this will be U2 minus U1. So W will be equal to 0.9. We have the value of U2. You input value of U1. You input 2 and 7. Okay, this is 97. What was the value of U1? Yes, that's it. So finally our work done will be minus 359.6 kilojoules because we have multiplied by the mass, so kilojoules not per kilogram. If you multiply with the mass, you will have the straight answer like 2323.6 kilojoules, 18 kilojoules per kilogram again. So just kilojoules, okay, just kilojoules. Now the heat transfer is 0 because it's reversibly adiabatic. Okay, now we'll assume that assuming it's an ideal gas. Okay, assuming it's an ideal gas, so let's write assuming it's an ideal gas, because we assumed it was a vapor. Now we are assuming it was an ideal gas. So P1 V1 T1 equal to P2 V2 T2. So remember, this is not applicable now, not applicable, so they don't need to write it. Okay, I can just decide to erase it so that I have space for another thing. Okay, since it's an isentropic process, we have our isentropic for an isentropic process. We have that T2 over T1 is equal to P2 over P1 all raised to power n minus 1 over n, where n is 1.4. Okay, so T2 will now be T1 P2 over P1 raised to power n minus 1 over n. So this will give us our T1 is 523. Okay, 523 P2. P2, what was our P2? 1.5, 1.5, and P1 was what? 15, I think so. Yes, 15. So got 1.4 minus 1 over 1.4. So that will give us 523, 0.1. It's about 0.4 over 1.4. So finally T2 will be equal to 270.8 Kelvin. So this is the final temperature. Now the work done. Remember, work done is M CV T2 minus T1. Okay, which is equal to U2 minus U1. So W is M. What was our mass? 0.9 times, you already know the value of this. Then T2 was 270. T2 was 270. 270.8 minus 523. So our work done will now be minus 162.9 kilojoules. Okay, kilojoules. The last but not the least is the heat transferred. But yes, this is an isentropic process, so heat is 0 because it is an irreversible adiabatic process. Yes, because it is a reversible adiabatic process.
It leads to liquor on some ladies. Yeah, we they turn up on a daily. It's how I walk up. Yeah, soft walk.